You ever write a line of code, maybe something really simple, and just stop and think, how does a computer actually get this? How do these words we type turn into a real working application? Well, today we're going to pull back that exact curtain.
All right, here's the game plan for this explainer. We're going to start with why we even need a translator in the first place. Then we'll meet the two main players, the interpreter and the compiler. We'll put them head to head, see how modern systems are getting the best of both, and finally, figure out how you choose the right one for what you're building.
So, let's start at the very beginning. At its heart, every single programming language, doesn't matter if it's Python, C++, or anything else, needs some way to speak to the computer's hardware. It needs a translator.
So take a look at this. Probably the most famous line of code in the world, right? Print hello world. To you and me, that makes perfect sense. But to a computer's processor, that thing only thinks in ones and zeros, in raw electrical signals. This is just nonsense. So how on earth do we bridge that massive gap?
Well, that's where this magic word comes in, translation. It's the whole process of turning our source code, the stuff we can actually read and write, into machine code, the only language the processor actually speaks. Without translation, our code is just a fancy text file. With it, it comes to life.
Okay, so with that in mind, let's meet our first method for doing this translation. Say hello to the interpreter, and the keywords here are fast and flexible.
So how does an interpreter work? Well, it's pretty straightforward. It reads your code literally one line at a time. It takes that first line, translates it, executes it, and then it moves on to the next one. It's this constant loop: read, translate, run, repeat, all the way to the end.
Here's a fantastic way to think about it. An interpreter is like having a personal translator sitting right next to you, whispering the translation of a foreign book into your ear, sentence by sentence. You get the story as it happens right then and there.
And because you get that instant feedback, this translate-as-you-go method is absolutely perfect for certain jobs. This is exactly why languages like Python and JavaScript, which lean heavily on interpreters, are kings in web development, scripting, and especially for just knocking out a quick prototype. You can make a tiny change, hit run, and see the result immediately.
All right, that's one way to do it. But now let's meet our second translator, the compiler. If the interpreter is fast and flexible, the compiler is, it's methodical, it's powerful, and it is all about performance.
Now, a compiler works completely differently. Instead of going line by line, it takes your entire program, the whole shebang, and puts it through this intense multi-step process. It analyzes everything. It optimizes the logic, and then only when it's all done, it spits out a completely separate, standalone file, what we call an executable.
So let's go back to our book analogy. The compiler is like a translator who takes the entire book and translates it into your language from cover to cover before you even read the first page. Yeah, you gotta wait a bit for that full translation to be done. But once you have it, man, you can read it smoothly and so much faster.
And that's the whole point. This method is built for one thing above all else: speed. We're talking raw execution speed at runtime. And that's exactly why it's the only real choice for things where every millisecond counts. Think high-performance video game engines, operating systems, and real-time control systems. We're talking languages like C++, C, and Rust.
Okay, so we've met both of our translators. Now let's put them in the ring, side by side, and really dig into the key differences and trade-offs. First up, how do they handle errors? An interpreter is kind of chill about it. It just starts running your code, and it'll keep going until, bam, it hits a bug, and then it crashes. A compiler, though, it's like a super strict proofreader. It will scan your entire program for syntax errors before it does anything else, and it will refuse to even create that final executable file until you've fixed every last one. All right, let's talk speed. And this is really a tale of two different kinds of speed. Interpreters are fast to start. You hit run, and it's basically instant. But because it's translating as it goes, the overall execution is going to be slower. Compilers are the exact opposite. You've got that slow, upfront translation time, that wait, but the program it creates, it runs wicked fast.
And what about portability? This is a huge win for interpreters. As long as a computer has the right interpreter program installed, your source code will run on it. Simple as that. Compiled code, on the other hand, is built for a specific target. An executable file you compile on Windows is just not going to run on a Mac. You have to go back and recompile it for every single platform you want to support.
So it really seems like a simple choice, right? You pick speed or you pick flexibility. But what if you didn't have to choose? In the world of modern programming, things have gotten a lot more clever, with some really cool hybrid approaches.
And this brings us to something called bytecode. Now think of this as a middle ground. It's like a pre-translated intermediate language. It's not the code we write, but it's also not the final machine code for one specific computer. It's this super portable, optimized set of instructions that's designed to be run by a special piece of software called a virtual machine.
And languages like Java are the masters of this. Here's how it works. Your Java code first gets compiled, but not into machine code. It gets compiled into this platform-independent bytecode. Then you can take that one bytecode file and send it to any computer that has the Java virtual machine, the JVM. The JVM then does that last little bit of translation for the specific computer it's on. You get awesome portability and way better performance than a simple interpreter.
But we can push this even further. This is where things get really, really smart, with something called just-in-time, or JIT compilation.
Okay, so while your program is running on that virtual machine, the JIT compiler is literally watching what's happening. It starts to identify the parts of your code that get used over and over and over again. These are called hotspots. And then, on the fly, it takes just those hotspots and compiles them all the way down to the fastest possible native machine code, and it saves that result. So what happens? The longer your program runs, the faster it gets, achieving performance that's almost as good as a fully compiled program.
So, wow, we've got interpreters, compilers, and these slick hybrid methods. With all these options, how do you even choose? Well, it always comes down to picking the right tool for the job. There's just no single best answer for everything. Let's make this super practical. If you're building a quick app prototype and need to make changes fast, an interpreter is your best friend. That immediate feedback is everything. But if you're building a high-speed game engine where every frame counts, you have to go with a compiler for that raw performance. And what about a big corporate app that has to run on everyone's computer? Windows, Mac, Linux? That's the sweet spot for the bytecode and JIT combo. It gives you that perfect blend of write once, run anywhere portability with seriously optimized performance.
And this kind of brings us full circle. The whole journey from simple interpreters and compilers to these incredibly sophisticated JIT systems, it just shows this constant state of evolution. Our demand for software that's faster and more flexible just keeps growing. And that makes you wonder, what's next? Will these lines keep blurring until they all just merge into one perfect translation method? Or is there some brand new idea out there just waiting to be discovered?